Hey, good morning, everyone. My name is Tom Douglas. I'm with RAECO. Thanks for joining us today on our continued webinar series. Today we have Ken Soleyn from GE. He's going to be leading us on a little introduction into moisture measurement. Ken's been in the industry for about 29 years and various instrumentation controls, including working as an analytical chemist, sales engineer, and a product manager for various chilled mirrors and laser-based analyzers. It's involved a number of organizations, including ISA, ISHM, AGA, ASHRAE, and NCSL, SL rather, and just a wealth of information. A couple housekeeping things. We would like to answer some questions throughout the webinar and towards the end. You'll notice in the GoToWebinar, like orange box on the right-hand side of your screen, there's an area for questions. So if things pop up, please enter those in there. We'll probably stop about halfway through and try to address a few questions. And then when we get to the end, we'll address any questions that we might have missed or any that have popped up in the second half. Again, we're going to make a recording of this available, so if you jump in late or you wanted to share this with a coworker, we'll have that available at raeco.com under our training page. You can also go there to see some of our past webinars. So without further ado, I'll pass over to Ken. Ken, thanks for joining us, and the floor is yours.
Good morning, everyone. As it was mentioned, we're just going to give an overview of moisture and humidity measurement and look into some of the various technologies for measuring. And then at the sort of down toward the end, we'll cover some of our most sort of popular applications. At GE, we have a fairly wide array of process moisture and gas instrumentation, everything from unitary sensors to analog transmitters that would say put out a 4 to 20 milliamp signal, to multi-channel analyzers and calibration systems. So in this map, we sort of see that the most simple sensors are generally lower in price but have very rudimentary features in terms of the product. They might just have a 4 to 20 milliamp output and no diagnostics, where the upper level instruments might have enhancements in terms of diagnostics and calibration and so forth. In looking at measurement fundamentals, the first thing we have to look at is, gas, because moisture or humidity is a gas. You're probably sitting in a room with somewhere in the neighborhood of 1 to 1.5% water by volume. Now that percent by volume is not to be confused with the relative humidity. That's just the volume of water compared to the rest of the gases. And here we see the composition of dry air, and of course dry air is mainly nitrogen. It's about 78% nitrogen, and the next to most abundant gas is oxygen, which is 21%. And each of those gases will exert a pressure directly proportional to its volume. So water is no different. If there's water in the environment, it exerts a partial pressure directly proportional to its volume. And the sum of those partial pressures add up to the total pressure. So we saw on the last screen that each gas had a partial pressure, and it'll contribute to the total pressure. So if we know the total pressure and we know the partial pressure of the particular gas, we can determine the concentration of that particular gas in a mixture of gases. And again, water is no different when we speak of it in the gas phase. If we have a closed system with liquid water in the system, the water will evaporate into the headspace, and there'll be an equilibrium between the liquid phase and the gas phase. And that headspace will become saturated, saturating meaning that it's holding the maximum amount of water in the gas phase. If we add any more water to that system, it'll condense out as liquid. Now, likewise, if we increase the temperature, we'll increase the amount that the space can hold. So as you increase temperature, you increase the amount of water that a given space can hold in the gas phase. And when it's holding its maximum amount, it's said to be saturated. And the water, of course, in the gas phase will exert a partial pressure directly proportional to its volume. So that value, that saturation vapor pressure, is very useful for us in determining how close the system is to holding its maximum amount of water, and anything in excess of that will condense out. It's important to remember that at the boiling point of water, which is normally 100 degrees C or 212 degrees Fahrenheit, that's where the liquid vapor pressure is equal to atmospheric pressure. And at sea level, of course, it's 100 degrees C or 212, but if we go into a higher elevation, let's say Denver, water will boil at a lower temperature because the atmospheric pressure is lower. Well, here are the equations for determining the saturation water vapor pressure, and the key variable here is the temperature. So that at a given temperature, we can determine the saturation water vapor pressure. Of course, you can put this equation into an Excel spreadsheet, or you can, there's several software packages. In fact, if you go to our website, you can download a program called HCon that'll run the calculation for you. And another thing to remember is that when that temperature T is equal to the dew point, the system is fully saturated. So we can also use this equation by knowledge of the water vapor pressure to determine the dew point, and likewise by knowledge of the temperature, we can determine the saturation water vapor pressure. So that's a key fundamental parameter for measuring moisture and humidity, is knowledge of the, or conversion to the saturation water vapor pressure. If we were to graph that out, we would see that it's an exponential relationship. As you increase temperature, the saturation water vapor pressure is increasing exponentially. And you can also see that if you, the bottom scale in temperature can also be thought of as the dew point. So if we have a dew point from negative 80 degrees all the way up to the boiling point of water, we're going virtually through 1, 2, 3, 4, 5, 6, 7, almost 8 magnitudes of measurement. So it's a very large dynamic range, and typically there isn't one particular technology that will cover the entire range. You might use different sensing technologies in the upper or middle range, and completely different technology in the trace range, in the very low concentrations. The dew point temperature, again, is determined as the maximum temperature at a given pressure where the gas will be saturated. And any surface colder than the dew point will acquire a dew or frost layer. So here we see the you can kind of see where my heart lies. Here you can see a frosted mug, but the surface temperature of that mug, of that beer mug, is colder than the surrounding dew point. So as water hits that cold surface, it will condense out. And again, we can run that equation sort of in reverse, and by knowledge of the saturation, or rather the water vapor pressure, we can determine the dew point temperature. The dew point temperature is important in a lot of industrial processes as a predictor as to when water will condense out. So very often you'll see specifications in dew or frost point temperature. If you increase the pressure, you will also increase the dew point. You have the effect of concentrating the water into less space. So that's important to remember, because very often we see into comparisons of various dew point instruments. And if you're into comparing dew point instruments, you either have to install them at the same pressure, or you have to make adjustments or calculations if the two instruments are at two different pressures. So this is often one of the things that we run across, is that people into comparing dew point instruments will often see large discrepancies, and if we query the process a little bit more, we might find out that they're not at the same pressure. So then we'll have to make some calculations to adjust for the pressure change. Relative humidity is the amount of water vapor in a given space compared to the saturation vapor pressure. And that's really just a dimensionless parameter. If we multiply it by 100, of course, we get percent relative humidity. And percent relative humidity is often used in the heating, ventilation, and air conditioning, or in industrial processes. For example, one that comes to mind is when they're coating phosphors onto CRTs or flat screen televisions. They do that in a very humidity-controlled environment to cure the chemical on the surface of the glass. And their parameter is in relative humidity. Absolute humidity is the mass of water vapor compared or divided by the volume. And very often you would reference that volume to a standard level. For example, in the natural gas industry, we speak about pounds per million standard cubic foot. And in the U.S., for example, 7 pounds per million cubic foot is the maximum amount of water you can have in natural gas for custody transfer. So we can determine the absolute humidity by knowledge of the water vapor pressure and the temperature. And the volume ratio is the amount of water vapor pressure compared to the total pressure. And there are two expressions of this. One is the volume ratio, where we're only talking about the water compared to the dry gas, and the other is the specific volume, where we're talking about the water compared to the total. Now, very often the amount of water is so small that the two values are very close together in low levels. When we get to part per million type levels, the E value is fairly insignificant. So very often the two terms might be used interchangeably. If we multiply those terms by 1,000,000, that's referred to as part per million by volume, which is a very common parameter. And the mass ratio is very similar, except here we're taking that volume ratio and we're multiplying it by the molecular weight of water, which is 18, divided by the molecular weight of the carrier gas. So this converts it to a mass-to-mass relationship. An example where that's used would be in engine testing, engine efficiency, and exhaust testing. One of the byproducts of combusting a fuel, if you take any fuel and burn it, if it's burned completely efficiently, you get heat, carbon dioxide, and water. So by measuring the water coming out of the process, you can back calculate or get an idea, and the term is called stoichiometry, of the efficiency of the engine. So there's an example where the mass ratio would be used. And again, if you pressurize the system, you're going to increase the partial pressure of the water directly proportional to the increase in pressure. So that volume ratio really doesn't change with increases in pressure. When you increase the pressure, you do increase the dew point, but you don't change the volume ratio or the mass ratio. The ppm stays the same. Now, there is a slight deviation to that statement when you get into very high pressures, because water is not an ideal gas. It deviates from the ideal gas, but it's a very small factor at lower pressures. You can see that that number, that constant, the K values are 3 times 10 to the minus 6. So they're almost close to 1 at low pressures, and they don't really come into effect until we get into elevated pressures. But these are just enhancements to correct for the non-ideal behavior of water. Our technologies can also be used to measure moisture in organic liquids, for example, in hydrocarbons such as oils or hexane or even refrigerants. The key is that we can only measure in non-miscible liquids. So, for example, somebody once asked me if I could measure the dryness of a martini with our sensor, and unfortunately you can't, because that's a miscible liquid. Alcohol or the gin or vodka mixes completely with water, so that would be a miscible liquid. We can only measure in non-miscible liquids. And these liquids have a degree of solubility per a fundamental relationship called Henry's law. The amount of gas that dissolves in the liquid is directly proportional to partial pressure over that. So by programming this data into our analyzer, we can directly insert our sensor in the liquid and determine the mass ratio, the mass of water to the mass of the carrier liquid, and it becomes a very convenient system for making that measurement. But again, to do this, you have to have knowledge of the solubility data. What's shown here on the screen, for example, is an example of Shell transformer oil, diala oil it's called, and that's used to insulate power transformers. Well, we're going to now go into a little bit about the various instruments. We're going to focus on the 4 technologies: the chilled mirror, aluminum oxide, which is used in very low levels of measurement, trace measurements, polymer-based humidity sensors, and TDLAS, which stands for tunable diode laser absorption spectroscopy, or we can just shorten that to laser instruments. And again, there isn't one technology that covers the full range of measurement. We can measure from minus 110 degrees C, which is in the parts per billion level, all the way up to 150 degrees C, which is higher than the boiling point of water. But there isn't one technology that'll cover that full range. In what we call the trace levels, which are normally below about 0 degrees C, we're typically using aluminum oxide sensors or laser or multi-stage chill mirrors. In the mid-range, from about 0 to plus 20 or 30 degrees C or so, we're using polymer capacitive sensors and our 1- and 2-stage chill mirrors. And in high humidity, we use polymer sensors and our heated chill mirrors. And heated chill mirror almost sounds like an oxymoron, but I'll explain that a little bit later. But it's a system where we directly measure the dew point temperature, but we have to heat all of the surrounding surfaces. So it's key to remember that very often there isn't one particular technology that'll cover the full dynamic range. If we look at a chill mirror, it's a fundamental instrument that measures dew point directly. And what we basically have is a mirror which is shiny. It's made of a polished metal. We use rhodium or sometimes platinum. And we have a light emitting unit, a gallium arsenide emitter, which is in the infrared. So it's much like the infrared signal that you use for a television remote control. And that light bounces off the mirror and is received by a photodetector. And hermetically sealed, we have another set that's at the same temperature and same conditions. And we use that as a comparator. So this sealed emitter and detector pair acts as a reference to what a dry, clean mirror looks like. We have a thermoelectric heat pump which consists of PN transistors, and as we run current through those, one side of it cools. And that heat is whipped away from the mirror, and the mirror cools. It'll cool down until to the point where condensation occurs on the mirror. When condensation occurs, the amount of light reflected off the mirror decreases. And when we see that loss of signal, the op-amp logic goes into a controller which modulates or throttles back the cooling until a bit of the dew or frost disappears. And it continues to do that until the system settles out and you have a constancy, you have a constant mass on the mirror. That temperature, when you have an equilibrium where the amount of water evaporating off the mirror and recondensing is at equal, the temperature of the mirror by definition is equal to the dew point. So what we have is a 4-wire platinum resistance temperature sensor embedded into the mirror block, and that has very good thermal conductivity between the mirror and the block. So that temperature by definition is directly equal to the dew point. And what the system allows you to do is, by making other measurements like temperature and pressure, is to calculate all of the other humidity parameters from the measurement of the dew point. Now, some of the key things with this is that it's normally used quite a bit as a reference standard for calibrating other systems. And the system generally has to remain fairly clean. It is forgiving, however, in that you can go in and manually clean it, and there are some automatic systems for cleaning it as well. The chill mirrors come in a variety of different configurations. There is more of an entry-level analyzer, and then there's an analyzer that's sort of a color display with various features such as data logging and digital telemetry, being both serial and Ethernet. You can access the analyzer from a remote location via Ethernet. And there are several sensors that you can choose from. The sensors are really rated by their amount of cooling capacity. The bigger sensors generally have more cooling, and very often the cooling is augmented with a built-in gold-plated heat exchanger where you can circulate a fluid. So if you want to measure down to dew points of -80 and below, you would typically use a water-cooled or liquid-cooled system. The heated chilled mirror, as I mentioned, heats all of the wetted surfaces except the mirror. And the idea is when you're looking at elevated temperatures, the mirror cools down just to the dew point, and it prevents condensation from occurring into the system. Chill mirrors are routinely used as primary standards for many labs. There's good interchangeability between the national labs of any country. So you can, for example, send a chilled mirror to NIST and have it calibrated there and use it as a transfer standard. The graphs here show just some data. This is just data from NIST itself that just shows the deviation from their standard. The graph below that, it was an interlaboratory study done a few years ago in Asia between 9 different Asian labs and NIST. So it was the a single unit was calibrated at NIST and put through a round robin of testing. And this graph to sort of the right here is a 7-year study showing the drift over 7 years, and it was certainly within spec after 7 years. Now keep in mind, in all of this data, some of the uncertainty of the measurement is due to the national lab itself. No calibration system, no matter how good it is without uncertainty. There's always some degree of error in any system, in any measurement system. The chill mirrors at our facility are calibrated using an automated process. We essentially use LabVIEW and a generator to generate known values of dew point, and then those are intercompared against the standard. So the calibration system offers us to provide a high repeatability and consistency in the products that are manufactured. We're also an NVLAP or NAVLAP accredited facility, 17025 facility, and our scope of accreditation is online. The next technology I'm going to talk about is aluminum oxide, and these are really industrial workhorse sensors, as I call them, for trace measurements. And much of the work we do, I would say probably about 70% of our sales in moisture and humidity measurement is for trace moisture or trace humidity. So in essence, we call ourselves, humidity, but what we're really measuring is lack of humidity or lack of moisture. There are many processes where a few part per million is too high for that process. For example, in ethylene production or in natural gas or LNG production, typically they may have alarm points in the neighborhood of 1 to 20 parts per million. There's some semiconductor applications where they start to get down into the parts per billion or even parts per trillion. So there's a saying that one man's desert is another man's monsoon, depending on the industry or the application associated with it. These sensors consist of an aluminum substrate, and on top of that is a aluminum oxide surface that's anodized on, and that oxide surface is very porous, and then on top of that is a very thin porous gold layer. As water molecules permeate into the superstructure, the water molecule is polar. It has a dielectric constant of about 80, and gases such as nitrogen or air have a dielectric of about 1. So essentially you can think of this as changing capacitance. Each pore acts as a parallel capacitor, and when capacitors are placed in parallel, you add them together. So essentially this functions as a water molecule counter. And as it absorbs more and more water, the capacitance increases. We measure the amount of signal out of the sensor by exciting it with a very low level AC excitation, and we measure the impedance of the sensor. And of course, impedance is a combination of the capacitance, resistance, and reactance, but the major contributor to the sensor's impedance is the capacitance. And this is just another picture of the sensor built up in it almost looks like a spark plug. There's a 3/4 inch straight thread that's normally covered with a shield, and you can see that the aluminum oxide sensor on the aluminum substrate. A few years ago, we went to a semiconductor manufacturing process where the sensor is now manufactured on a wafer. So you'll see some newer sensors that look like the one on the left, and the older sensors, on the right, and the older sensors look like the one on the left. These sensors can also be outfitted with an integral pressure and temperature sensor, so you can measure those parameters simultaneously and use the fundamental dew point measurement to calculate the other parameters, and very often the analyzer does that for you. This is the calibration curve, and with each sensor we supply a calibration curve at 14 points. We actually test 10 points and then calculate out a 14-point table. So this data will either be provided on a piece of paper where you input the data into the analyzer, or on our newer sensors. I say new, but the sensors that have been out for, like, say, the last 7 or 8 years, they have a module that stores the data directly on the sensor. There's a memory chip that stores the data, so those sensors become plug and play. So as a sensor is used, it may shift a little bit, and you can send the sensor back for calibration, and you'll get a new calibration curve, or a new calibration embedded into the sensor. So very often we have a saying that these aluminum oxide sensors, an older sensor is a better sensor because it's proven itself out. And if you send sensors back to us on a regular basis, you have the data to show what the drift over time is in a given process. All of that data is stored in our archives and our electronic systems. Now, aluminum oxide sensors take considerable time to dry down, but they wet up. You can think of them as almost like ceramic sponges. They will wet up very quickly, and like a kitchen sponge, if you were to have a bone-dry sponge on your sink, you can wet it up very easily. Just put it in a sink with water. But to dry it out, you'd have to squeeze it out and then maybe put it into the sunlight or something to have it dry out, and maybe by the next day it would be completely dry. Well, you can think of that as being similar to the aluminum oxide sensor. It does wet up very quickly, but takes considerable time to dry out. But notice that most of the change happens very quickly, even on the dry out. So we often talk about the 90% step change as the rate of change when we reference the rate of the sensor. A number of our instruments have an enhanced response, and we're able to improve that response by a fairly good magnitude. Here we show a step change to 1 ppm from ambient conditions, and without the enhanced response time it took about 50 minutes. But with the enhanced response time it only took 1.5 minutes. And the way it does that is it looks at the slope, or the rate of change, and by looking at the rate of change it's effectively able to predict where the sensor is going to end up. So this becomes very useful on a dry down situation, particularly where you have a large delta T. It works very effectively for that by using this rate of change slope measurement as a way of predicting where the sensor is going to end up. The aluminum oxide instruments come in a variety of different configurations, the simplest being a probe with a linear analog output. We also have it packaged in an explosion-proof process transmitter, as well as with analyzers with intrinsically safe barriers. So the analyzer can be either put into an explosion-proof enclosure or a safe area, and then the probe is connected via an IS barrier built into the analyzer. And there are also a number of portable instruments that are available. The portable instrument is very useful for spot checking. The yellow one you see here has a built-in desiccant chamber where when the sensor is not in use, the sensor is stored in a dry environment. So the sensor is sort of pre-dried, and it gives you a faster response. So something like that might be ideal for spot checking. The calibration system for our aluminum oxide sensors is a very automated process. We do thousands and thousands of calibrations. The sensors are ramped through 10 discrete dew points, but before we even do that, we dry everything out. And this complete process takes about a week to do. All of the data is stored in our archive, so if you have one of these sensors, you just need to go online and enter the serial number, and you have access to the history behind that probe. So you can register online and access your probe's history, and all of that is kept in our archives, our enterprise system. Well, with that, I'm going to maybe just take a break and open it up for questions.
And again, probably the easiest way is to use the question box you have on the right-hand side of your screen. And if we don't have any, we'll carry on until we get to the end and take any questions at that point.
Do polar molecules affect the aluminum oxide sensor the same way?
I didn't hear that. Could you speak up?
Yeah.
Please.
Yeah, so when we're talking about the aluminum oxide, the capacitive approach, what about related molecules like alcohols or similar polar molecules? Do they fill those sites in a similar fashion, or is it very selective to water itself?
That's a good question, and you're correct that they're not, because those will have a polarity similar to water, and you'll get a combined effect. So, for example, if you had methanol, let's say in a natural gas pipeline, the effect of that methanol will cause a higher than actual dew point reading. The aluminum oxide couldn't really discriminate between the methanol and the water. Now, when the methanol goes away, the sensor will return back to normal, but you would be uncertain as to what that total effect was. In some applications, they refer to that as the process dew point. The process dew point is the combined effect of all the polar compounds. And very often that might be used because it's somewhat repeatable.
But that's not the case. The laser has the ability to discriminate between polar compounds and the water itself.
Right. Specifically for alcohols like methanol and others, the laser technology works on a bit of a different principle. It's more like a fingerprint, where it's able to discern the water peaks separate from methanol or other alcohols. Now, there are some co-absorbers in laser technology at particularly low levels, and we're going to come up on some techniques of separating out the water signal from some of those co-absorbers as well.
Thank you.
That's an excellent question.
There was one other question was thrown in here. Someone was using the stage chilled mirrors as a reference for standardizing other portable sensors, and they're curious about how often they should expect to clean the mirror.
If you have ultra clean gases, we've seen where you don't have to clean the mirror except maybe once a year or once every 6 months. However, you can't have too clean of a mirror. When our operators, in our calibration systems, because we use the chill mirror as a reference, we clean the mirror prior to every run because you can't over clean the mirror. So we always know that we have a good starting point. And cleaning the mirror is a fairly simple process. You're just putting distilled water or distilled water with a bit of methanol on a cotton swab and swabbing the surface of the mirror while it's heated. So it becomes a routine thing for us on every calibration run. But it's overkill. We don't have to do it. We could probably not clean the mirror except maybe once a year, because our gases are very, very clean. We're using nitrogen boil-off. In more industrial processes, there's some industrial processes like automobile exhaust where you clean the mirror once a day. And we have an automatic system for cleaning the mirror as well called the pacer cycle, where it will automatically do some of the cleaning.
Sounds good. I think that's kind of the questions right now, so probably just keep plugging on.